briefly explain a color calibration part again. Okay, basically I didn't specify how we get the color correction matrix. Basically we just use, I want to measure these color checkers, and we measure it, and after white balance and normalization, we use an optimization algorithm to find a color correction matrix that can, to the best I can, map the original colors to the standard color checker, and we basically apply that matrix to the original image to, in a way, expand the canvas. And so, in theory, this process will be undue when we display the image on e-papers. So that will make the output image a little bit closer to the original image. Any other question?
Hello. I was curious when you said the color correction is highly nonlinear,
Yeah.
and then you export the mathematical model to correct it, and it seems to work. But I'm curious why you didn't use neural networks for this problem, because they are famous to be quite good at nonlinear problems.
Why did I choose neural network?
Why did you not choose neural networks?
Why did I not choose that? Because that I did thought about it, but I'm not very educated on neural networks, so I didn't choose that. Maybe I could try.
Okay.
If I study for 2 more years or something.
Okay, maybe you can leave it to the next one.
Okay. Due to limit time, we welcome the second speaker. Who is the second speaker?
谁是第二位讲者？于右成。你是吃掉左边。Okay, let's find. Let's find this.
我先吗？好。Okay. Hello everyone. I'm going to start in my report. My sound is not great because I got a flu. Okay, so hello everyone. I'm Yu Ming Ho. I'm a student under the guidance of Professor Jiabing Wang. And the title of the paper I'm presenting today is Research on Coexistent Analyzing Modeling of B2X and LAA in heterogeneous network and wireless resource allocation based on reinforcement learning. And the research is divided into 7 chapters, which are introduction,
numerical basis, system model, proposed algorithm, simulation result, conclusion, and reference. So this is motivation. Okay, in the recent year, the data traffic of mobile communication device has increased significantly to satisfy the broadband mobile international demand. The LTE, long time evolution, and 3GPP, third generation partnership project group purpose mobile communication technology to provide a high data transmission rate solution. Using a license band to increase transmission speed is a future trend. The NR small cell and V2X will be deployed in the same file or integrate into the same machine and compete for the use for a license band. Since LAA will gradually suppress the bandwidth used by V2X users, making it a fair competition has become an important issue. Because of limitations of human sense, the user satisfaction is seen as a new evolution to maximize the user's profit. Before delving into the details of the research content, we need to first understand the applied models and the theory, which are the LAA Wi-Fi transmission probability and user satisfaction. To efficiently utilize more substrate resource, 3GPP introduced part of a license band to increase the mobile broadband service. The first is LTE-U, the second is LAA, and the third is LWA, and the fourth is ELAA. There are four properties to deliver packet, which are shown as follows. The property 1 is the most important property to ensure the user basic or emergency demand be met in time. And property 2 is used to streaming media, those who need low delay and high bandwidth. And property 3 is used for command internet application, which can be waited until property 1 and property 2 are done. Property 4 is used for background programs like download, event, or renew apps. Our V2X network has already been constructed on this band and time sharing system. Time sharing system is called distribute coordination function, the DCF, which used energy detection, ED, to determine non-V2X system and using dynamic frequency selection, DFS. Distribute coordination function, DCF, plays a major role in the study. The TXOP is a parameter that can determine the transmission route of LAA user. In the reference 2 shows that the TXOP is one of important factors directing racial resource allocations in the coexistence between LAA and B2X networks over a license span. Taking the ratio directly as fairness index will make it difficult to estimate the range of fairness countries. Estimate the range of fairness coefficients, and German fairness index is introduced. This index is usually used as a reference for fairness when a multiple user provide transmission resource service, so we can take into account the right of our users while maximizing resource utilization. And here is our system model. This is the a schematic diagram of heterogeneous network. Here, we assume that B2X and LAA have an equal number of users with a limit distance range under the 5GHz frequency band. They compete for transmission in a point-to-point manner. Building on the simulation environment from the previous page, Wi-Fi's LAA's distribute coordination function, DCF, is an extremely important transmission machinist from B2X users. The Markov two-dimensional chain model shown on the right row V represent the various possibilities of B2X transmission success and failure. The first equation on the left column indicates the probability of decrementing in the reverse order at the same level. The second equation represents the probability of counting down to 0, succeeding in transmission, and returning to the minima content window. And the third equation indicates the probability of transmission failure and transitions to the next level of contention window under the state of level J-1. The fourth equation represents the probability of transmission failure at the last level is n+1, and returning to the minima contention window level. This is the transmission for LAA, as shown on the same page, is represented by the Markov two-dimensional state transition diagram on the right, which similarly depicts the various possibilities for the transmission success and failure. The first equation on the left column indicated the probability of decrementing in the reverse order the same level. The second equation represents the probability of counting down to 0, succeeding in transmission, and returning to the minima contention window. The third equation indicates the probability of transmission failure and transitions to the next level of contention window under the state of level is j minus 1. And the fourth equation represents the probability of transmission failure at the last level is m plus EL. And returning to the minima contention window level. This also includes the concept of the retry limit. So, in the reference to using the ratio as state will reduce both of the performance of LA and the B2X users, lead to average poverty. To avoid the situation, Jan's throughput fairness index is introduced, which can be applied to any user, defined as the following. And this is the fairness index throughput, like this. And this is my model, like this. Okay, now, reinforcement learning. The reinforcement learning is mainly through rewards, R, and the observation, O, to determine subsequent action, A. And at the same time, an agent will be trained to find an optimal policy that can handle the environment to obtain the best reward R. The agent chooses the best action for the environment state is S. Next, I will introduce the DQ network, DQN, in the reinforcement learning, compared to Q-learning used in the reference. QL uses a table to store the Q value for each action in every state. However, the problem today is too complex. The number of states can be numerous as the star in the sky. For example, in playing Go, if we were to store them all in the table, even the largest computer memory might not suffice. Moreover, searching for a specific state in such a large table would be very time consuming. However, in a machine learning, there is a method well suited for the task, namely neural network. We can treat state and action as input to the neural network, and after the network process them, it outputs the Q values for the action. This way, we don't need to record Q values in the table, but can directly generate Q value using the neural network. Another approach is to input only the state and output the value of all possibility action. According to the principles of Q-learning, we directly choose the action with the highest value as the next step. We can imagine the neural network receiving external information, similar to how eyes, nose, and ears collecting information, which is then processed by the brain to output the value of each action. Finally, an action is chosen through the process of reinforcement learning. Next, we will analyze based on the second type of neural network. As we know, neural network need to be trained to predict accurate value. So, how is the neural network training into reinforcement learning? The first, we need the correct Q values for the action A1 and A2, and we substitute this Q value with the Q target. Used previous used previously in the Q learning. Similarly, we also need a Q estimate to update the neural network. Therefore, the parameters of neural network are updated by talking the old neural network NN parameters and adding the product of the learning rate alpha and the difference between the Q target and the Q estimate. During the training process, the new S state and it corresponding A action and R reward will be up.
You have to skip some.
Okay, will be observed. The new Q value will be calculated and the next state will be updated. Then alpha is referred to learning rate as follows, like the picture. And this is the James Fairness Index in the reference 1. And this is my model. Then alpha is a parameter that can be freely adjusted from 0 to 1, determining whether the outcome will learn more toward fairness or total throughput. That the normalized diff is absolutely value of the difference between LA and B2X, while the normalized sum represents the sum of LA and B2X. As alpha approaches 0, there will be better throughput, and as alpha approaches 1, there will be better fairness. And this is a proposed algorithm.
You have to finish the speech in 3
Okay.
minutes.
Okay. This is the.
You can skip some.
Okay. This is the.
Skip.
Okay. This is my model. Then this is my state, and this is my action function, and this is my reward function. So this is and this is our simulation parameters. And this is the comparison including the individual throughput of B2X and LA, as well as the algorithm throughput using the recombinant TXOP adjustment of Q1 and LBT. And this is the Q-learning Q1 and Q2 compared. And this is my model. When A was 1 and when A was 0, then the picture like this compared. And the conclusion. Based on the result discussed, the original algorithm can save the most resource that ensure that the fair distribution. However, under the premise of fairness, it is impossible to simultaneously consider the overall throughput. Therefore, we have created a model that allows for a choice between fairness and maximizing overall throughput. This way, users can adjust the parameter alpha to freely determine their own needs. And this is my reference. Thank you, everybody.
Okay, question? have to have much more practice. 你要多练习，多练习。Okay? Although this a presentation in a seminar class, you have to serious consider just like the difference, just like the 就像你的口吃一样，OK? Okay, due to limited time, we welcome the third speaker.
Okay, good morning everyone. I am your Professor Gao Wenzhong. Today I will introduce data compression of multi-pigment color electronic paper. Okay. This is outline. First we will introduce the electronic paper, and then I will introduce preprocess and definition, compression flow, and the final is result and conclusion. This is a brief introduction to electronic paper. I just call it e-paper. And the first speaker has already provided a general overview, so I will not go further on that. My research focuses on the use of the billboard on the right with my mouse. This one. And I will provide a more detailed explanation of this device. This type of e-paper is commonly referred to as uncolor e-paper. The operative principle is shown as below image. It's worth mentioning that this device can only display even specific colors. Therefore, regular image need to be converted using a technique such as dithering to make them compatible with this device for display. And you can see there is 7 colors: red, green, blue, and yeah, only 7 colors. Okay, why is compression necessary? Imagine that we need to display a large advertisement on e-paper, like the one shown in the image, just this, or even larger. This will require a significant amount of memory space. However, current mainstream image compression methods are only suitable for regular images and are not suitable for e-paper images. Therefore, developing compression methods specifically tailored for e-paper image could reduce the storage space required by hardware device, thereby lowering costs. Additionally, if the conversion process does not require complex computation, it can further reduce hardware costs. Considering that the human eye is less sensitive to high frequency images, and that the device size is small with the resolution of only 800 by 480. This study treats 2 pixel by 2 pixel plot as one unit. If the method proposed is in this research are applied to larger e-paper size with higher resolution, and the block size could be adjusted to 3 by 3 or 4 by 4 or larger. Before compression, we need to perform some preprocessing. We will ask the device to divide the image into 3 layers. You can see here the 3 layers, including background layer, object layer, message layer. Yeah, background layer is a large scale layer that usually does not contain important information. And the object layer includes prominent objects that attract attention, such as people, cars, house, animals, and etc. And message layer contains important information such as phone number, address, product price, like this. After reward, each layer will be converted into image suitable for display on e-paper through methods such as color mapping and filtering. And this action will this other way you can see below here. This is out. So my research is focused on compression. So this is ours. Okay. And then in each layer, pixels covered by other layers will be deleted to reduce redundancy. And you will notice that in the case in this car, there's no pixel has been deleted because no pixels of the car are covered by other layers. You can see if this word golden stage covered by car, we will delete some pixel from this car. Okay, and next, each layer will be divided into blocks of 2 by 2 pixels. Okay. Check if any blocks in all layers contains both the valid pixel and the transparent pixel. Transparent pixels refers to pixels in the image that are not part of the display content. If such blocks are found, transfer valid pixels from the layer below. It's worth nothing that if layer N, okay, layer N, I'm so sorry about that. Okay. It's worth nothing that if layer N is the image layer and the object layer has no valid pixels, then valid pixels will be fixed from the background layer. After preprocessing of image, the next step is to define the standard codebook. A standard codebook compares all unique blocks that the e-paper can display, with duplicate removed. And for example, this black, white, black, black, and black, 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 white, their looks are same. So we just only contain one. If a block contains only one color, there are 7 such possibilities. For block contains 2 colors, 2 colors, 1 color is 7, 2 colors, 3 colors, and 4 colors. We add together and then we can get 210. If we project all the blocks after mapping onto the CIA LED color space, we will also obtain 210 distinct colors. The LED color space is designed to quantify the color perceived by human eyes. And next step is the comparison process. Firstly, we will statically analyze which blocks appear in the image and record their frequency of occurrence, along with determine which layer each block belongs to. And you can see, for example, this layer is 0. It means it belongs to background layer. This is 1 belongs to object layer. This is belong to message layer. And this is comparison follow, and we will introduce. Maybe the word is very small, but I will read it for you. The first step, we will combine same LB blocks, and then we will setting sample codebook size. I introduce this first. Okay. Combine same LB block. For example, this block and this block. If it becomes very small, it will looks same for human eye. So we will delete this and add this time to this. And you will notice that sorry. You will notice that with the block with a lower layer index, after checking all blocks, the size must be not exceed 210. And then we will create a simple code book. And its size is shown as in the figure. 128 it means 7 bits, 64 means 6 bits, 32 means 5 bits. Okay. And now after we do these two actions, and then we will check the number of blocks in message layer is less than 128. If it's not, we will fill the simple code size to 256 and copy the original code book, and then we just start the comparison. If yes, is more than 128, we will check the number of blocks of the message layer is less than size of simple code book. If it's no, we will make a size of simple book times 2 and then come back. And next, we will check the size of original code book is more than 32. And notice this, if the size of a code book is less than 32, we consider that in this case, deleting any block will result in significant loss of image quality. Therefore, we will fill the code book size to nearly power of 2. For example, if the current code book size is 10, we will fill it to 16. If the current code book size is 22, we will fill it to 32. And if it is more than 32, we will do vector quantization. Okay. Before I introduce vector quantization, I will introduce this cost function. This cost function, after creating the original code, we define the cost function. Yeah, this is the local cost function here. X represents any block marked as belonging to background layer or object layer in original code book. The message layer is excluded because in general, it only displays essential information and does not allow distortion caused by color changes. Why? Why represent all blocks in the original code book except for X? And below is delta I. Delta I represents the distance in LAB space between each block and the other. It's important to note that the L multiplied by 2 to account for the devices, static colors, and the human eye's sensitivity to brightness. W of X represents the layer weight, with a weight of 1 for background layer and 2 for the object layer. P of X represents the probability of the block appearing in the image. K of X represents the reciprocal of the number of combinations of layers in which the X block appears. As the number of blocks of one layer decreases, X of X increases. The global cost function. X is each block in original code book and Y is each block in a new code book, which is composed of the standard code book. We will search for a similar block in a new code book to each in the original code book. The distance between them in the LID space is represented by delta E. If the colors are same, then the delta E is 0, of course. We calculate the delta E for each block and combine it with other parameters to obtain the overall global cost. defining the cost function, we will proceed to determine which block should be included in the final code using vector quantization. And next, the original code. Before we start the vector quantization, we can see the original codebook can be divided into two parts, message layer part and outer layer part. And then all the blocks from the message layer are placed into the same codebook. And remaining the codebook are determined by local cost function. For example, if we still need 10 blocks, we calculate the local cost using the local cost function and select the top 10 blocks from original codebook to add to the same sample codebook. Choosing the top block helps spread out the block of the sample codebook in LAB space. After creation, all blocks from original codebook are clustered based on the block in the sample codebook. Continuously arrange and replace all the blocks within each cluster until convergence is achieved. After convergence, each block in the sample codebook is compared to blocks in the standard codebook, and it is replaced with a closed codebook from standard codebook. And finally, calculate global cost function to quantity distortion. And this is final codebook. Finally, each block 2 pixel by 2 pixel in the image is matched with the closest block in the final codebook and store the index completing the compression process. For the compression, it's just a matter of restoring each block according to its index, making it straightforward process. Okay, and now is result. Before I show the result, we should know the compression rate. First, we calculate original data size first. My device, resolution of my device is 800 by 418, and every pixel 7 colors, so it uses 3 bits, and then we can get 144,000 bytes. And after compression, there is 2 parts of the data. One is codebook, and one is picture. Codebook, for example, if codebook size is 256, and every box needs there is 4 pixels in every box. Every pixel needs 3 bits, and then we can get 384 bytes. In picture size, resolution is 800 by 418, and the box is 2 by 2, so we divide it first. And then, because the total size is 256, so we need 8 bits, and then we can get 96,000 bytes. And we add together, and we can get almost 67% of original data size. And if codebook size is 128, we can get 58% of original data size. If codebook size is 64, we can get 50%. Almost the conversion rate is 2. If our codebook size is 32, we can get 42% almost. Okay, and I show you the result of image. This is original picture, and this color belongs to object layer. And its golden stage belongs to message layer. And left image it is original image after uploading, we need to change it to ePaper image. We just call it ePaper image. And right side is we put this image on this device. This is before compression. And this is after compression and decompression. And you can see there is little difference, but you almost can't see any difference on this device. And this picture, we This picture of copper size is 128, and the conversion rate is 1.71104. Yeah. And this is another image. This car, white and black car, belongs to object layer, and this PUAL, yeah, this is L. It belongs to message layer. Left side is e-paper image. Right side is we put this image on it. This is after compression and decompression. The copper size still 128. And this red car belongs to object layer, and the Fourier belongs to message layer. It belongs here. And this is e-paper image before compression, and this is after compression and decompression. And note you can see the copper size is 64, and because we don't need too much color, and the conversion rate is almost 2. And the explosion, the red car belongs to object layer, explosion belongs to message layer. And this is before compression, this is after compression and decompression. And note this copper size is 256, and it's over the standard copper size, so there is no global cost. And the conversion rate this is still type of conversion rate 1.494. And this is our future president. This image is before compression. This is after compression. The conversion rate is still 1.7104. Okay. The maximum purpose in this paper achieves a compression rate of up to 67%, even the worst case scenario. However, it's worth noting that while the global cost function is used to calculate the distortion level of the image, it's not utilized during the process of deleting redundancy. There may be other optimization algorithms based on deleting redundancy that could further reduce image distortion. Noise is also uncertain. You can see, for example, you can see the sky. Oh, sky. I have no much time, so. Noise is also a concern. It's observed that the compression induces a lot of noise into the image. This is because restoring the image from the limited number of blocks can read to this image. I have attempted to address this by randomly rearranging the pixel within each block during the distortion. However, this approach doesn't fundamentally solve this problem. If we could establish a set of rules to determine the arrangement of the 4 pixels within each combination in image, it might be possible to address the issue. Nevertheless, it might be a challenge to notice such a noise on larger e-paper displays. Okay, this is reverse. Thank you for attention. I finally finished it. Okay.
Any question?
More question?
Okay, thank you for presentation. So I just wonder, because e-paper is still not common today in our daily life, so our first speaker is also using e-paper. Are you using the same e-paper as the first person?
No.
No? Okay, so I just want you to briefly introduce about the e-paper you use, okay?
My paper is uncolored. The first CB used e-paper named CFA, and it's how to say about it? Okay, I introduce my first. this device of paper named N color, and every pixel only 7 color, every pixel. And CFA further stick used, and it's a little strict. For example, the first pixel is red, second is blue, and third is green, and so on. And every pixel it has 16 scales. Yeah, so
Okay.
it's different, very different.
Okay.
Thank you.
Thank you.
More question?
Okay, this one.
How do you send image to the e-paper?
You mean put this image to e-paper?
Yes, because I'm confused about you use the strategy of image compression method, which means that you might transmit this image far away from that have a long distance from e-paper.
Actually, I'm little not understand what was your question, but after comparison, we got two part of data. One is code and other side is this picture after encoding, and we put this data to the memory on e-paper device, and then maybe we can design a circuit or something chip to the compression here. And you can see it just the code and picture, and we just only to maybe the first data is 16, and we can search the 16th code and then recover it. Very easy. Just this.
Can you speak in Chinese?
You are not.
用中文讲。
等一下，你在讲是那个你中文想问什么？
哦，
问题是嘿，
就那个，
哎，
就是你是怎么把那个影像，就是传到 e-paper 上面显示出来的？因为你的PPT 上面讲到了那个影像压缩，通常影像压缩就是像是远距离传输讯号过去，所以它需要进行影像压缩，然后再把它还原过来。
可以这么讲，我们有一张原图，然后我先经过压缩，我压缩完之后，我会把它变成就是当这两个 codebook and picture， 它就是两个档案。maybe 我可以把它用在 USB 里面，然后我把它塞到那个 e-paper 的那个装置上面，然后 e-paper 里面那个装置就一些小电路，直接读取这些资料，然后直接在装置上直接做解压缩的动作。
那是硬体的吗？
对，它是硬体的，所以我可以事先存好几张图，然后直接塞到，因为它已经变很小，我就直接把它塞到那个 e-paper 的装置上，这样可以大幅压低那个我 RAM 所需要的空间。如果我一张图直接塞进去，没有经过压缩，不会需要这么多的空间。OK。
Okay, thank you. We welcome the next one. 周宣国。
Good morning, Professor and students. I am Shenbo Cho. I am pleasure to be here to share this research with you. This is the topic of the research, dynamic object tracking and prediction of floating points. This is the outline of today's presentation. First, I will give a brief introduction about research motivation. Then we will move on to our method, color conversion, polynomial fitting, coordinate conversion and decision tree. And in the end is conclusion and reference. In this study, the image recognition function is used to find the target, and the initial velocity, elevation angle, azimuth angle, and distance of the target are calculated from the two images obtained by the webcam. The experimental data is classified through the decision tree to predict its landing position. This is the system flowchart of my experiment. First, I use computer to receive images and identify objects and capture image through webcam. Second, read historical image and current images, and then perform image processing, including color space conversion, color feature extraction, erosion and dilation. Third, calculate initial velocity, elevation angle and azimuth angle. Final, through the calculate data into the decision tree model to determine the location of the landing point. Color space is a way of expressing color. Common color space include RGB and HSV. In this study, converts the image from RGB to HSV in order to convenient feature extraction of the image. This article uses this method to paint the phone end of the badminton red. Use color feature to detect red as a target. Displace the matching value with white dot and change other value to black dot. However, similar colors will also be judged as red, such as brown and orange. So upper and lower limits need to be set to reduce the possibility of misjudgment. In order to eliminate noise in the image, use erosion and dilation. First, read the original image. Second, set the structure element n and the number of iteration. Because of the structure element used in this article is 4x4, so take out 16 pixels in the structure and perform add operation. As long as there is a pixel, there is a 0. The center point pixel is changed to 0. And final output the image. And I is the original image. The erosion operator represents the add operation. And n is the structure element. The difference between dilation and erosion is that the OR operation is used. One of the pixels has a value of 1, and the center pixel is changed to 1. Erosion is done first to eliminate noise, and then dilation to enlarge the target. Because there is only one camera, and the distance range of badminton is wide, and I use monocular ranging. Use the pinhole imaging principle to measure and consider the internal parameter of the camera. Using similar triangle, we can get the formula. And according to the table, you can see that there is an accuracy problem. We can see that if exceed 100 centimeter, the error will exceed 10%. In order to solve the problem, polynomial fitting was added. First, collect image at different distance. Find the corresponding pixel width through feature extraction. And use polynomial fitting on this data to find a curve that approximates the data. And I used 216 sets of data and performed 3 fittings. In order to estimate the distance of the object in the photo, it needs to be converted into world coordinate. And first step is convert pixel coordinate to image coordinate, then to camera coordinate. Final turn to world coordinate. OP is the origin of the pixel coordinate, which is in the upper left corner, and the unit is pixel. OF is the origin of the image coordinate, which is the optical center of the camera. Unit is millimeter, and dx dy are how many millimeter each pixel is in the image. The conversion process from image coordinate to camera coordinate is from 2 dimensions to 3 dimensions. F is the distance from OF to OC, which is the focal length of the camera. Then use similar triangle to write the relationship. ZC is obtained by monocular distance measurement. Camera rotation represented by the rotation matrix R is a 3x3 matrix that describes the directional relationship of the camera to the object. The 3-dimension coordinate of the camera center in the world coordinate are expressed as a 3x1 translation vector T, describing the positional relationship of the camera to the object. After the world coordinates are pressed through the rotation matrix and translation vector, the camera coordinate can be obtained. And pixel coordinate to world coordinate, first step is the result of the previous merger, and the second step is matrix processing. In the third step, this article assumes that there is no rotation, so that R be the unique matrix, and there is no translation vector T. Let T be the 0 vector, then we can get world coordinate. The decision tree is added to improve the accuracy of predicting the landing point. In this study, divide the badminton landing point into 3 areas, left, center, and right. And then 50 pieces of data are obtained for each block, and 80% for training, 20% for testing. X1 to X6 are the world coordinate, initial velocity, elevation angle, and azimuth angle of the second frame of badminton. The output label 0 represents the middle area, and label 1 represents the left area, and label 2 represents the right area. And finally, use the confusion matrix to evaluate the model result. Green indicate correct and white indicate error. It can be seen that the test accuracy rate is 80%. And conclusion, this study completes a set of badminton landing point classification based on decision tree, and combining polynomial fitting and monocular ranging implementation result. This is my reference. Thank you for attention.
Okay.
do you calculate the speed of badminton?
And I use 2 photos to calculate the distance. And I know how many frames between the 2 photos. And I can get the time and divide them. Thank you.
How do we use the decision tree to determine a setting point?
Here you can see I have 6 input, and decision tree will select the most obvious feature of classification, and it can divide them into 2 categories and continue the same steps until there is an output label. Yeah, thank you.
Hello. I'm curious about how do you calculate the camera parameters?
How do I calculate the camera parameter?
You must set the camera to the position, and you can use the formula on the PPT.
Which page?
Next. And yes.
Yeah.
Yes.
This is the formula. You can because we need to pixel coordinate to word coordinate. Then the process is 3 stages. First is pixel coordinate to image, and then we need to image to camera coordinate, and the final we need to camera coordinate to word coordinate.
Yes. I mean is how do you calibrate your camera？ 就是你怎么去经过这个相机校正，来得到这个相机参数？
是用棋盘格。
哦，OK。
Thank you.
Okay, next one.
Anyone?
Next one is Xu Minhan.
Hello everybody, my name is Xu Minhan. I'm from CIRL Marco. I'm Professor Xu Chenjian's student, and my research is on online action detection. And this is my outline. In introduction, I will say what is online action detection, this test. And in challenge, I will say I find 2 challenges in online action detection and method. Because of these 2 challenges, so I use a method to improve online action detection model. And this model I choose LSTR. LSTR is online action detection's famous model. This is supervised learning. In introduction, I will say what is online action detection. In a category, it's only for example, if you want to detect 2 actions, run and jump. If you want to detect 2 actions, run and jump, and you will have three categories. Background means you are not run and jump are your target action, and background means not your target action. If not your target action, and this is background. And input is on-screen video. For example, if now is frame, each frame has one level, and if now is time is 2, so you need to predict the frame 2 what action is right now. And because frame 2 not run and not jump, so frame 2 is background, and the on-action detection input will be the frame 1 and frame 2. And if now time is 3, and now the label is wrong, and your input can be frame 1 to frame 3, or your input. And in on-action detections, they all do a K+1 classification. The K means your target action which you want to detect, and +1 is the background. The background means if not your target action, then it is background category. And LCR, TRN, GitHub is a prominent model in on-action detection. And this TRN, you can see here, this is TRN's probability distribution. It is his output, and P0T is the background. So TRN is K+1 classifier. And LCR is the same. Here is his output, K+1 classification. And GitHub, here is his output, C+1 prediction. So the same is the C+1 classification. C and K is the same. So number one challenge is it has a data imbalance because each frame has a label. And for example, if the action is, for example, if K is 3 action, I will have four categories need to label. And the background label will label many things than other action, because you can see the picture like that. So this is the only example. So background will label many. So this data imbalance is very big. See, here only K is 3. If K is 10 or 20 or 30, the background will very, very big than other action. This is number one challenge. And before I say number two challenge, I need to say what is classification. In AI, in machine learning, supervised learning has two ways. Two things to do. One is regression, one is classification. And in classification, we are doing classification, not recognition. So if I want to classification the image cat and dog, I only need to find a difference between cat and dog. I don't need to recognition what is cat, what is dog. I only need to find a difference. So the K+1 is the on-action detection test. The left is K classified. In a K classified, if I only want to classify run and jump, in supervised learning, my model only need to learn how to classify. My model only need to find difference between run and jump. So maybe I see your two legs is not touch the ground, and then you are jump. So it's easy to run. And if have a background, if the RIT can have a background, maybe I need to find a difference between run and jump and background. The background, the background means is not your target action. And if your target action is run and jump, so background means not run and not jump. So actually in K+1 classified, my model needs to learn the difference between run and jump and not run and not jump. So if my model need to know what is not run and not run, that means they need they need have my model need have deep understanding on each action. It need really know what is wrong, what is jump. So this is very hard. This is not to challenge. Any method. First I training action classifier in K action classifier. The test is action recognition, not online action detection. So the input is string video. And this action classifier, K action classifier, is easy to train because it is K classifier. No background problem. And number one challenge is data imbalance. You don't have data imbalance. So this is very strong. This can easy to train. And then I put it on here. This is LCI, is online intelligence model. I put it on here. And get a probability of K action and input to LCR. And I put in the reconnected layers, the first layer. Oh, I freeze it. When I training okay in here and in here I freeze it. No training here. I training okay and put it here. Or I won't train LCR. Okay, but why I use this is good because this is beginning. LCR need to output the K. For example, if K is 2, LCR need to do the 3 category. And in our method, I put here K action classifier because this is easy to train, so this will be very strong. Now input label will now input LCR is wrong. So K action classifier can easy to get it is wrong to LCR. So LCR don't need to know it's jump. It only need to say, oh, it's wrong or not wrong. It's wrong or background is enough. So it's easy. So as my LCR only need to learn is this action or not this action. So the problem will be easy. If now it's input is background. And K action classified because he don't have background, so maybe he also say wrong. But the label is background now, and here is wrong. So LCR only need to say it's wrong or background. So the problem will be easy than the beginning. And this is my result. In online detections, have 2 data sets. They all compare with 2 data sets. One is Lemmas 14, one is T series. And this is Lemmas 14's data set. And I compare it in here. And it is my false and it means every decision. And Lemmas 14 have 20 actions. This is my result. This is my conclusion. Number one, I find 2 challenges in online communication. And number 2 is I do most online communication train the paper market price. But I think we need to first determine the action before checking if the action has occurred. Because that will let the problem be more easy to learn. And this is my result. And I have forgotten to the reference. So thank you.
Any question? No question? Can you go back to the comparison? You compare jump, run, and background only? Only run or background?
No, I target action. This is only. Sorry, can I speak Chinese? 我做20个动作，但是这个是只是想要解释说为什么我这样做。所以其实没有20种。对，我是在最后这个 扔的只是资料集上，然后这个是 RF indication 的 database，RF indication 比这两个最喜欢的。
只是为什么它的那个
这些都是你们实验室的。
对对对。
那实验室的话，像比方说这边这些
我没有讲到这个，因为对，就是一些比较细节的地方都可能可以参考。因为那个是比较细节的，我就没有报出来，我想说报那个原理就好。
因为
讲概念。
因为看起来就是你们的方法都是大概都70分以上嘛。那这些的话都是那个
LTI 改的。
OK。Any question?